This lesson is intended to introduce you to the concept of a limit. Now, a limit is something that is used pretty much as the basis of calculus in grade 12. Before we look at what a limit is exactly, I want you to consider in previous lessons when you had to determine the average gradient between 2 points. In those cases, you would have been given a point, say now x equals 1 and y is equal to 2, and x equals to 2 and y is equal to 5. And if I asked you to calculate the average gradient between those points, in essence what you were doing was calculating the gradient of the straight line that joined those 2 points together. So in essence we've been working out the average gradient between 2 different points. Now what I want you to think about now is, what would you say if I asked you what is the gradient at one particular point on this curve? So for example, if I just gave you that point and I said what is the gradient at that particular point? Your initial reaction could be, and actually should be, that it's not possible to define gradient at a particular point because it's just one point, and we then don't know in which direction the graph should go from that point. But if we look immediately to the left of that pink point and we look immediately to the right of that pink point, we can see that the gradient is fairly consistent on either side of that point, which would imply then that the gradient at that point is something very similar to, if not the same, as the gradient immediately to the left and immediately to the right. So in this case, the gradient at that pink point is a fairly positive steep gradient. Similarly, if I place the point at the turning point of the function, and we look immediately to the left, and we look immediately to the right, you'll see that to the left the gradient is decreasing as it gets closer from the left-hand side to the pink point, and on the right the gradient is increasing as it moves away from that pink point. And I'm sure you'll be able to agree with me that at that pink point there is no gradient because the graph is stationary. It's a turning point of the parabola. But now how do we work this out algebraically? Let's start with a random point of x equals 2. Right, so I'm going to choose this point of x equals 2. And then give this function a name. So this function is in fact f of x equals x squared plus 1. It's a parabola. So to calculate the y value when x is 2, we would substitute the 2 into f of x and get a y value of 5. So in essence, we know that the point we're dealing with is actually here on the curve. Now, how do we determine the gradient at that particular point using this information? Well, we're going to start with some experiments. So let's take a value immediately to the left of 2. So for example, if we take this value here of 1 and we substitute 1 into the function, we're going to have f of 1 is equal to 1 squared plus 1, which is 2. And if we take a value immediately to the right, let's say 3, and we substitute 3 in, we're going to get 3 squared plus 1, which is 10. Now those two numbers on their own don't really seem to help. But if I show you a table where we've substituted many smaller decimal numbers on either side of the x value of 2, we can begin to see a pattern emerging. Right, so if you look first at the top half of the table that I've shown you here, this deals with values that are smaller than 2, in other words, to the left of 2. So if you look on the graph, starting just to the left of 2 and moving in a negative direction. And in fact, the table there has started with x equals 0. So they've started at this point. So when x equals 0, substitute 0 into the function and we get a y value of 1, which you can see on the graph. When x is 0, y value is 1. Now we've taken the x value of 1, which we did just now, and we got a y value of 2, which is shown over here. And then what they've done is they've started to go in decimals, so 1,5, 1,6, 1,7, down to 1,9, 1,99, 1,999. So I want you to see what's happening here. These values are getting closer and closer and closer to 2. 1,9999999 is very close to 2. And look at these values on the right-hand side. What's happening to the y values? As the x values are getting closer to 2 from the left-hand side, the y values are getting closer to 5. Right? So we've gone from 1 to 2 to 3,25 to 4,24, 4,96, 4,999, 4,999, 4,quadruple 96, and as you can see, we get closer and closer to 5. We don't actually get to 5 because we're looking at values that are less than 2, not 2 itself. Then if you look at the bottom half of the table, we now have values that are greater than 2. So they've started at 3, which is what I used earlier as well. And they've got, for x equals 3, there should be a y value of 10 over here, not 9. All right, so that should be 10. All right, and then you can see the same kind of things happening. As we are moving from 3, x value of 3, down to 2.5, remember, because we're going from 3 towards our x value of 2 over here. We're going 3, 2.5, 2.4, 2.3, all the way down to 2.000078125. So understand that this point is very, very, very close to x equals 2, but to the right of 2, so it's somewhere here. Whereas this value here, 1,99999, and so on, is very, very close to 2, but just to the left of it here, and we're getting closer. So look what happens to the y values. They become closer and closer to 5 as well, from 10 to 7,25 to 6,26 to 6,29, and so on, all the way down to 5,0000125, getting closer and closer to 5. So in both of these cases, the numbers of the y-axis, the y values, are getting closer and closer to 5 from a negative direction, that's from the left, and from a positive direction, which is from the right-hand side. Right, so how do we represent this algebraically? We say that the limit as x approaches 2 of this function. Okay, so x equals 2 is actually our x value that we want to find the limit at. All right, what is the maximum y value that that graph can get to, whether it approaches x equals 2 from the left-hand side or x approaches 2 from the right-hand side. So in this case, they've actually given us the function as x squared plus 1. You must use a bracket when you have more than one term in your limit. Otherwise, if you didn't use a bracket, then it wouldn't show that the 1 is actually part of this function and part of this limit. So all we have to do now, algebraically, we don't have to do those hundreds and hundreds of substitutions as you saw in the table on the previous page. But all we have to do is substitute x equals 2 into this particular value over here. So the limit as x approaches 2, we're going to substitute the value that we want the graph to approach into x squared plus 1. Right, so we're going to get then x equals 2, so it becomes 2 squared plus 1, which is equal to 5. So remember, we didn't actually get to 5, a clean whole number on the table, because we didn't actually use the value 2. And it's important at a later stage to realize that we can't always have the gradient at a particular point, but I'll explain that as we go along. So in this case, the way we would read this is that the limit of f of x as x approaches 2 is 5, meaning again that as the x values approach 2 from either side, the y values are also approaching 5 from either side. Right, so now we're going to look at some algebraic examples of how to deal with limits. Right, firstly, example A. Determine the limit of 2x squared plus 4 as x approaches 1. Right, straightforward here. All we need to do is substitute 1 into wherever we see x. So it'll be 2 times 1 all squared plus 4. And notice that the moment I substituted the value that x is tending towards, in other words, this value here, I've now dropped the limit notation. Right, so then this simplifies to 6. Okay, example B. Determine the limit of x squared minus 4 over x plus 1 as x approaches 2. Right, also straightforward, we can substitute straight away. So in our numerator, we're going to get 2 squared minus 4 over, in the denominator, 2 plus 1. That simplifies to 0 over 3, which is then 0. Example C, determine the limit of x squared minus 1 over x minus 1 as x approaches positive 1. Now this one isn't as simple as it seems. What I need you to see is if I had to just go and substitute, and I'd put 1 in the numerator in place of x, so 1 squared minus 1, and 1 in the denominator in place of x, we get 1 minus 1, we actually get 0 over 0. Now this is not a helpful expression at all because it's undefined. It has a 0 in the denominator, so we have to figure out a different tactic in order to solve this one. Right, so when you encounter a limit like this where the x value that you're intending to substitute will give you a 0 in the denominator, you need to first see what else you can do. You need to manipulate the expression. And one of the most common things that we can do is to factorize and cancel before we substitute the limit. So now in the next step, we're not going to get rid of the limit. We're going to keep that there because we haven't substituted it in yet. Yet in the denominator, we're going to leave that as x minus 1, but the numerator is a difference of 2 squares. So that becomes x minus 1 and x plus 1. And then you can see that the two x minus 1s will cancel, and you'll then be left with the limit as x approaches 1 of x plus 1. Now remember, put that x plus 1 in a bracket. Now we can substitute, and we will not have a problem in that we won't have anything undefined. So we can then show, well, as x approaches 1, we can substitute 1 into x to end up with 1 plus 1, which is equal to 2. Now to explain practically what's happening here, we've converted this original complicated function into a simple straight line function. So if I had to draw that straight line function, it would look something like this. Okay, the function x plus 1 would look something like that, going through 1 on the y-axis. All right, but because in the original expression, the value of 1, so I'm looking here, if x was 1, would make this graph undefined, which means that at x equals 1, this graph cannot exist. So at x equals 1, I'm going to put 1 here on the x-axis. We know then that this graph actually doesn't exist there. So we're going to erase this part of the graph. And at the point where x equals 1, we actually have an open dot, meaning the graph doesn't exist at that particular point. Now, you're not really expected to sketch this when you're asked to solve a limit, but it's useful to understand how the graph would look. So although we've cancelled it out and turned it into a straight line function, and it was always a straight line function, it does have a restriction in that x actually cannot equal 1 on this graph. So the limit of this graph is still 2, meaning that the values to the left and to the right of this graph when x equals 1 are approaching 2. But in this case, they can never actually get to 2 because at 2 it's undefined. I hope that makes sense. Right, if we look at example D, we're going to see a similar thing occurring here. So they're asking for the limit as h approaches 0 of 2h plus 3 all squared minus 9, and that's all over h. Now, in this case, again, you cannot substitute h equals 0 into the expression as it stands because we will have a 0 in the denominator, which is then undefined. So there are two ways that you can do this. The first way is, and again, remember, we keep the limit notation now because we are not substituting h yet. So there are two ways that you can do it. First of all, we can multiply out the numerator. So we're going to have that bracket then becomes 4h squared plus 2h times 3 is 6h. Double it, we get 12h. And then 3 times 3 is 9. And then we have minus 9 over h. Right, and then now what you see happens is that the two 9s cancel out. The positive 9 and the negative 9 cancels out. So that means the remaining two terms both have an h in, which we can then factorize in the next step. All right, so still keeping the limit notation there. And by the way, while we're using the variable h, you'll see that h has quite an important meaning in calculus, which you will get to in a further lesson when you deal with the derivative of a function using first principles. Okay, but that's for another lesson. Okay, so factorizing that h at the top, we end up with 4h plus 12. Now you can see that the two h's will cancel. This h and that h will cancel. So we're left with the limit as h approaches 0 of 4h plus 12. And now we can substitute h equals 0. So it'll be 4 times 0 plus 12. Notice that I'm now dropping the limit notation because we've already substituted our h value. And that equals 12. But I did say that there's another alternative to solving this one. And that's to recognize that, in fact, the expression that you have in the numerator is a difference of two squares. Alright, so this 2h plus 3 all squared minus 9 over h is a difference of two squares. So we can factorize that as such. And really either or method is fine. It's whatever you're comfortable with. So we have 2h plus 3 minus 3. And we have 2h plus 3 plus 3 over h. So in this case, this one's a little bit more complicated, in my opinion. But again, both will work. All right, so if we simplify the first bracket, the 3's cancel, so we're actually just left with 2h. In the second bracket, we end up with 2h plus 6 over h. And now again, the h's will cancel, so that you're left with the limit as h approaches 0 into 2. So I don't need the fraction line. So it'll be 2 into 2h plus 6 with those h's cancelled. And now you can substitute the 0. So it'll be 2 into 2 times 0 plus 6. So in the bracket there is just 6, and therefore 2 times 6 is 12, which gives you the same answer. Right, example E is the limit as x approaches 3 of x cubed minus 27 over 3 minus x. Now in this case again, we cannot just substitute the x equals 3 in, because you're going to have an undefined denominator, so we need to factorize. And you're going to have to refer back to your grade 10 and 11 notes, unless you've already done it in grade 12, how to factorize a cubic or a sum or difference of two cubes. Right, so I'm going to leave the denominator out for now, simply because I'm going to show you how to manipulate that in the next step. But first, in order to factorize a difference or sum of two cubes, we know that we're going to end up with a binomial and then a trinomial. So for the binomial, we are going to take the cube root of both of the two terms as well as whatever sign is in the middle. So that gives us x minus 3 in the first bracket. Then in your second bracket, the trinomial, the first term, the one that goes here, is always the square of the first term in your binomial. So that is x squared. For your second term, you multiply both of these together and give it the opposite sign of what's here. So multiplying the x and the 3, we get 3x, and the opposite sign is positive 3x. For the last term in your trinomial, the one that goes here, we square the last term in the binomial to get positive 9. So your last term in the trinomial will always be positive when factorizing a sum or difference of two cubes, and these two signs will always alternate, that one and that one. Right, so why I left the denominator out is I want you to see that the x minus 3 that we have here almost looks like the 3 minus x in the bottom. And the idea here is that we want to cancel the denominator out so that we don't have to worry about the undefined problem. So all we need to do here is to factorize a negative out the denominator so that we end up with x minus 3. Now the two x minus 3's look the same, and we can cancel them. So to tidy up, before I substitute the limit, we are going to remove the denominator. We're going to put the negative at the top to give us x squared plus 3x plus 9. And now we don't have any undefined problem, so we can substitute the x equals 3 into our expression. Right, so it's going to be 3 squared plus 3 times 3 plus 9, and that gives us 9 plus 9 plus 9, which is 27 times the outside negative gives us negative 27. Right, last example is example F, and this one is a different one, but an important one nevertheless. So the question is, as the limit of x approaches 2, as x approaches 2 of 7. Now in this one you'll see there are no variables in the expression, so there's no x, so there's no way to substitute 2 in. So in this case, the answer is simply 7. All right, and that's because there's no way to substitute it into the expression x equals 2, so it'll stay the same. Now to give you an understanding of what this example means, if we had to draw the graph of y equals 7, remember that this represents the limit of x approaching something of f of x. So in this case, f of x is 7. That means it's a horizontal line that goes through 7 on the x-axis. So that means when x equals 2 over here, the y value is 7. When x equals 3, in fact, the y value is 7. In other words, it doesn't matter what the x value is. Whatever x is approaching, the y value is always going to be 7. So if you have the limit as x approaches something of a constant, then the answer is simply equal to that constant. Okay, so I can put that in a different form for you to say that the limit as x approaches any value, let's call it a, of a constant equals that constant, whatever it is. Right, to end off, before we move on with limits, this is a small exercise for you to do in order to just practice the concepts, etc., and then we will move on at a different stage.